Okay, so we're going to start Math 151 here. We ended up with doing some integration in Math 150, and really we only had two options in terms of integrating things. We either knew them from the formula from the basic antiderivatives, or we used what we called USUP, right, which we're still going to use. It's extremely useful, very easy to use, very popular, but we're going to expand that, and we're going to now talk about some other techniques of integration, and that's the subject of this first exam. So this first technique that we're going to discuss here is called integration by parts. There are some analogous methods or techniques that match up with differentiation, and this is one of them. So you can see here that the chain rule for differentiation, that's where the U-sub comes into place. That is kind of the opposite for integration. So it turns out that integration by parts is really the reverse of the product rule. So it might be useful to review the product rule. Hopefully you remember this, right? So you have two functions multiplied together and you want to differentiate them. It's one times the derivative of the other plus the other times the derivative of the one. So we can easily figure out the integration by parts formula by just integrating both sides of this is really what we're going to do, okay? So integrating the derivative simply cancels out, and we get this situation here, and then a little rearranging, we get our formula for integration by parts. Okay, so there it is. So basically the integral of u dv is equal to uv minus the integral of v du. So when you're given your integral, you're just going to have to figure out what is my u, what is my dv. U stays the same, v is the antiderivative of dv, and then of course the v goes there, and du is just the derivative of u. So as per usual, we'll go through a couple of examples, and then I'll leave you to work on the worksheet and the homework problems. Okay, this is if you want to write it out the long way with f of x and g prime as opposed to u and v and dv. It doesn't really matter, whatever works for you. So here we have our first example. Now the other thing too is, when do you use integration by parts? Well, remember, it's kind of undoing the product rule. So if you have a product of two functions, in particular if you have a product of a transcendental and an algebraic, what are those again? Algebraic is, you know, the root functions of polynomials, things of that nature, and transcendental is the trigs, exponentials, and logs. So this is a classic integration by parts here. We have x times sine of x. Now again, one of these we have to pick to be our u, and the other we have to pick to be our dv. Okay, and the question then is obviously, well, what are we supposed to pick? In general, you want to pick the u such that du gets easier. It's not always the case, but it's most of the time. Okay, so of this one, which one gets easier? If u is x, is the derivative easier, or if u is sine x, is the derivative easier? Well, obviously if it's x. So that's what we're saying here, right? Basically it's getting easier. So if we figure out or pick that u is going to be x, which indeed it is, that makes dv sine of x. And then how do you figure out du and v? Well, du is just the derivative of u, which is obviously 1, and v is obviously the antiderivative of sine, which is minus cosine. And then you kind of set it up. So that's what we've done here, right? So u is x, du is 1, dv is sine, so v is minus cosine. And then just putting it into the formula, right? It's uv minus integral of v du. Okay? And the idea is, this integration we don't know, it's not immediately obvious or easy to do, but this one is, right? The integral of cosine, when you take out the minus 1, is something you should know. It's just sine. So there you go. You know, technically, it says here, technically if u is x, the derivative is 1 dx, right? The derivative plus c, technically, but we're going to assume c is 0. That's essentially what this part says here. Okay. Now notice if we did it the other way, if we let u be sine x and dv be x, you would set it up and you would actually get this, and you would know to stop here and discontinue this, because this is actually worse than what we started with. Okay, you want to, the basic idea here is to set it up in such a way that the derivative and the resulting integral is easier. Okay, clearly this is not. Now this is a good time to talk about this particular function, right? We have not talked about the antiderivative of the natural log, and the reason we haven't is because technically you need to use parts. Okay, well, how would you use parts? Ln of x is one function by itself. Well, it's perfectly okay to let dx be dv. So you would let u be the ln of x, and dv would simply be dx. In that case, the derivative, you should remember, is of course 1 over x. And the antiderivative of dx is just x. Okay, the antiderivative of 1 is x. So setting up our uv minus the integral of v du, we get this. Okay. So there is the answer to the question, what's the antiderivative of the natural log of x? Okay, you needed parts. That's why we didn't talk about it before. Let's take a look at this example here. Little more complicated than the first one we started with, in that instead of an x sign, we have an x squared and a cosine. M is just a constant here. So again, which one of these gets easier? U is definitely going to be our x squared, which makes du 2x dx, right? Or just 2x is fine. dv is going to be cosine mx. And be careful with v, because if you're going to integrate cosine of mx, technically it's a substitution. It's a simple one, but it's a substitution nonetheless. So u is mx, and du is m. So you need an m inside and a 1 over m outside. Okay, so it's actually sine mx over m. Okay, so putting that together, u times v minus the integral of v du, we get the following. So that's what we have here. Put this together, and this is what we get. And now, is this integral something that we know? Well, no, not off the top of our heads, but did it get easier? Yeah, because you see the degree of x went from 2 to 1, so it is actually getting easier. So what you can do is take this piece by itself and do integration by parts again on that. So it is possible that sometimes you can do it twice, or you need to do it twice. For the purposes of this course, I will never make you do it more than twice, because that's just not cool. It just becomes very tedious. But we still need to evaluate this, so you just simply do parts again. Call capital U x and capital DV sine mx, and it's the same process. You can go through it and take a second. And then putting it all together, you'd get this, which looks pretty substantial, but it's not that big of a deal. Okay. And then there's one final example that I want to go over. Now, please understand that this example that we're going to do here is a rare case. It doesn't happen very often, if at all. You'll see maybe 1 or 2 in the homework or in the review, but usually you don't want to start with this. Okay, if you have to do parts more than twice or once even, you might want to just take a look and make sure. Now, the problem with this, which you may have noticed already, is that both of the functions are transcendentals, right? The derivative of neither one of them really gets easier. In fact, the derivative of e to the x doesn't change, and sine x just keeps going back and forth. So this potentially looks like it's a problem, but let's see what happens. So if we let u be e to the x, and dv is sine of x, that makes du e to the x and v minus cosine. And so we put that together and we get this, and the resulting integral, as we guessed, is no easier than what we started with, right? It looks like we've gone absolutely nowhere. But if we just take a look at this and let's just try this, and let's just do parts on that piece. Again, u would be e to the x and dv would be cosine. And so you get e to the x for du and sine for v. Putting that together, we get just the integral of e to the x cosine dx, which again, doesn't look like it got easier. However, if you insert this piece here, this result in for this, let's take a look and see what happens. Something sort of interesting. So you combine those two things, and you get that the integral of e to the x sine of x is equal to some stuff minus the integral of e to the x sine of x. Notice that these items are the same. So I can add that integral to both sides and get 2 of them on the left. Right? That's what I've done there. I've just simply added that integral of e to the x sine of x over and gotten 2 here. And then divide by 2, and you can actually get your answer. Right? So we can figure this out. This doesn't happen often. It happens when there's 2 transcendentals. Sometimes it works. Again, standard parts is usually the way to go most of the time. I'm just showing you this, because it may pop up occasionally. So there in a nutshell is integration by parts. All the examples that we did actually were indefinite. All of them had the plus C. You can do the same thing for definite. Just make sure that the bounds go on the UV part also. Okay, and you'll practice that in the worksheet and the homework. Again, these are pretty straightforward. The first one I'm actually telling you what U and DV are, setting it up for you. These are going to want to select what U and V are, but hopefully it's pretty obvious what the U selections are for B and C. Again, DU wants to get easier, and they're very similar here for the homework, right? We're going to evaluate some. I'm giving you the first one here, and then the rest you're going to go ahead and choose. And this looks a lot like the ln of x example. And this looks a lot like what we just did at the end, right? Two transcendentals, you might have to do it twice.